In this video, you'll learn how you can use quantitative predictors and indicator variables to predict a binary response variable using multiple logistic regression. Until now, we looked at regression models that describe or predict a quantitative variable, but there are also regression models for ordinal and nominal response variables. In this course, we'll discuss only binary response variables, for which we use logistic regression. Remember the example where we predicted popularity of cat videos with the predictors cat age, hairiness, and presence of a cat in costume? Suppose I wanted to send in some of my cat videos to the International Cat Video Festival. Each year, out of approximately 10,000 videos, only 100 videos are selected and shown. If I could get my hands on a random sample of the 10,000 videos from last year and determine cat age, hairiness, and costume, I can see whether these variables help to predict what videos get selected. So the response variable is 1, getting selected, or 0, getting rejected. This is what my data look like in a scatter plot if I look at just the predictor cat age. We see that younger cats seem to get selected more often than older cats. How can we model this relationship? A straight line would be inappropriate since it results in estimated values other than 0 and 1. A discontinuous jump function like this looks good, but it isn't ideal for mathematical reasons. We need a continuous, smooth function. The logistic function, which has a sigmoid shape or S-curve, is a good choice. It produces estimated values that lie between 0 and 1. This means that we have to redefine our predicted variable. We're not predicting getting selected in terms of zeros and ones, but the probability to get selected. We'll change the continuous predicted probability back into a binary variable later on. All cases with a predicted probability of 0.5 and higher are predicted festival selections, and all others are predicted festival rejections. But first, let's see what the logistic model looks like. Here's the equation at the population level. If beta is positive, the curve goes up. If beta is negative, the curve goes down. The size of beta determines the steepness of the curve. The horizontal location of the curve is determined by both alpha and beta. The value minus alpha divided by beta determines at what value of x the inflection point lies. This is where the predicted value is exactly 0.5. Why this logistic function, and how do we find estimates for alpha and beta? Well, the logistic function has some nice features. By transforming it, you can change it into a straight line and use the formulas for linear regression to calculate the intercept and regression coefficient. First, we take the odds of getting selected. This is the probability of getting selected divided by the probability of not getting selected. This might seem to complicate matters unnecessarily, but if you go one step further and take the natural logarithm of the odds, also known as the log odds, or logit, the equation simplifies to a linear function. You don't have to be able to follow along with this. You just have to understand why we use the log odds, because it gives us a linear function. Also, when you use statistical software to calculate the intercept and regression coefficient, they're reported in log odds. Let's look at the output for our first example, predicting festival selection with just cat age. The log odds regression coefficient estimate value is not very easy to interpret. It represents the linear change in log odds with a 1-unit change in the predictor. The intercept and regression coefficient estimates are often also reported in terms of odds. Since the model in terms of odds corresponds to an exponential function, the regression coefficient can be interpreted as a ratio. It indicates by what multiplicative factor the odds will change with a 1-unit increase in the predictor. It says by what percentage the probability of getting selected versus not getting selected will change if the cat is 1 year older. The regression coefficient expressed in terms of odds is therefore also called an odds ratio. In this case, the odds to get selected decrease with about 28% with every 1-year increase in cat age. If the odds are not reported, we can calculate them from the log odds by raising e to the power of the log odds. We can manually calculate odds and probabilities at particular ages, for example at age 2, by using the exponential or logistic function. If you find the logistic function hard to work with, you can also calculate the probability by dividing the odds by 1 plus the odds. The other output includes the standard error, z-test statistic, and the p-value. The test statistic is a z-value, not a t-value, since we're modeling proportions, not means of a continuous variable. The interpretation of the test statistic and p-value is the same as in linear regression. The relation between cat age and festival selection is not significant here. We can add quantitative predictors and binary indicator or dummy variables, just like in linear multiple regression. As you can see here, adding the predictor hairiness and the indicator costume doesn't help. None of the predictors are significantly related with festival selection, while controlling for the other predictors. One last bit of output that can be very useful is the classification table. This table shows the number of rejected videos that were correctly predicted to be rejected and were incorrectly predicted to be selected. The percentage of rejected videos that were correctly predicted to be rejected is called the specificity of our model. The table also shows how many of the selected videos were incorrectly predicted to be rejected and were correctly predicted to be selected. The percentage of selected videos that was correctly predicted to be selected is called the sensitivity. Obviously, we want both to be high, just like the overall percentage of correctly classified cases.